Okay. All right. So how you guys doing today?
Good, how are you?
Good. Perfect. All right. So let's start chapter 4 again. Okay. So we talked about some the chemical reactions in aqueous solutions. We had a couple examples we tried last time. There's another one you can try. Okay. So we have lead nitrate, potassium iodide. Okay. And then we can try to do this one here. So first thing what you need to do, once again, you're gonna do double displacement. Okay, these two. So you can have this and this combination. So you can have a new product on the other side. Okay? So that will make this one lead iodide, and then you have a potassium nitrate here. So I'm gonna just write it this way. Okay. So now you have to think about this one has a 2+ charge, and this nitrate has -1 charge. That's why you have 2 nitrate for that over here. So if you have this one and this one, this is a +1, potassium is +1, iodine is -1 here, so it's 1, 1. But if you just pair these two, you're going to have PbI2, because if you look at the iodine, is on the second last column in your periodic table, means it's going to be a negative in ion form. So you're gonna have a -1 here, but this is +2. So to make one neutral compound, you have to have a 2 iodine, not 1, for each lead elements over here. If you look at the potassium and nitrate, this is +1, and this is -1. Okay. So this is why you have just 1 potassium, 1 nitrate. That's okay now. Okay. This is 1 plus -1. That's okay. So now it's good, but now you can try to have a 1 over here, and then you have if you have a 1 rectus over here, you have to have at least 2 potassium nitrate, because this one has 2 nitrate in this compound here, but you have to have a 2 potassium nitrate, because each potassium nitrate has only 1 nitrate inside. So that makes 2 at minimum if it's 1 over here. And then if it's 2 at minimum, it makes also 2 potassium on the right side. So I'm gonna put 2 here to make the same number of potassium, and also iodine here, because there will be 1 compound here, will be 2 iodine here, so it'll be 2 potassium iodine, 1 lead, 2 nitrate, 2, 2. So we're good here. Okay. There's one more thing I want you to think about, is the solubility. Okay. If you think about the solubility in water, this one is going to be soluble in water because of this nitrate anion is always soluble in water, always. So if you have a potassium nitrate, sodium nitrate, calcium nitrate, whatsoever, if it's a nitrate paired with the nitrate anion part, that compound will be always soluble in water. So in that case, this is also a soluble in water. Okay, so this is an aqueous form here, and this one is also in aqueous form because of the potassium. Potassium is group 1 element. So if you look at the potassium in the first column, those are the ones that makes all compounds soluble in water. No exceptions. So this is why potassium iodide is also soluble in water. So it'll be in an aqueous phase, means they're in ion form here. Means they will dissolve in water. This one, how about this one? Can you guys guess? It's a potassium nitrate. It will be soluble in water or not? Perfect. Because it's a potassium or nitrate, they're both soluble, really good. So aqueous phase 2. But the problem is this one. You have halogen, but halogen most likely soluble in water with some other type of a cation part. But I don't know if you guys remember this. This is one of the exceptions you have. Either silver, lead, and mercury is the exception. So if a halogen bound to any one of those 3, it's water insoluble. Okay, so this is the water insoluble. Okay, So this iodine is also in the second last column, this halogen. So any halogen group, group 7, usually 90% chance water soluble. But those 3 exceptions that makes those compounds with the halogen groups insoluble in water. Only 3 exceptions. Okay, so this will become in solid phase, meaning it will not be dissolved in water. So they will actually come out from the mixture. Okay, so this is why you're going to see this precipitate, and this process is what we call precipitations. Okay, so if you write this one again in 4 ionic equations, what happened to this one is actually this one. Okay. Goes to precipitate. Okay. So if you look at this one here, this one and this one didn't do anything. Okay. Here they're all same on the both sides, left and right. So those are the one that we call spectator ions. Spectator ions, okay? Means they didn't do anything. They're just watching, or just they stay the same on the before and after. So what actually done is those 2 making precipitate. So this is what actually happened. But they're just there because it's a mixture. Okay. So if in this 4 ionic equations, if you just try to remove this the same spectral ions on the both side, you're going to have your net ionic equations. So your net ionic equation will be looks like. So net ionic equations explain what actually happened in the reactions. Okay, this will be just this one. Okay. This is what actually happened. Okay. See, this one is once in the aqueous phase, all of these are in water, but when they come together, they become precipitate. Because now water is soluble. So this is what we call net ionic equation. So even though you look at the chemical equations, 4 chemical equations, if you remove all the same ions on the both side, which is the spectral ions, you get down to the only one that actually do the reactions. That is our net ionic equation. Just this. So let's do one more. Okay, and this time I'll let you try, and we can do this together anyway. Don't worry about it. Okay, so I'll give you about maybe 2 minutes. So let's try calcium nitrate and potassium carbonate. Try this one, okay? So once again, it's pretty much the same. Do the outer and inner combination, cation and anion part, and try to balance each element in the compound so you can have a neutral charge on the products, and then balance the equations and see if there's anything that is water insoluble from between one of your the products, okay? Okay, I will go back 2 minutes. Try the inner and outer combination and try to pair it with their formal charge. Okay, so once again, this is a -1. Calcium is +2, right? Because it's in the second columns, and this is a +1. Carbonate is -2. Okay, so try to pair up and try to use their formal charge to make the each right numbers of the elements in the compound, and then you balance each elements on the both side. Okay. Okay, about 1 minute. So we'll do this together. Don't worry about it. I just want you to try it on your own first. That will make more sense when you compare your answer to mine. Okay. Okay. Okay, so let's do this together. So I'm just gonna do the same thing what I just did here, just the calcium carbonate and potassium nitrate, because it's inner and outer, so we can do the perfect double displacement reaction over here. So I'm gonna write the products. So there'll be calcium carbonate, and then I'm gonna put the potassium nitrate. Okay. Luckily, here's the thing. This is -2 plus 2. Oh, I'm done. Right. So it makes neutral just 1, 1, okay? But this one is also kind of lucky with +1, -1. So 1, 1, no, that's good. So we don't have to do anything, it's already neutral here. So only thing you really need to do is you have 2 potassium and 1 potassium carbonate, because this is +1 charge, -2, there had to be 2 potassium and 1 potassium carbonate. So even though you have a 1 over here, you have to have 2. Because each potassium nitrate has only 1 potassium, but 1 potassium carbonate has 2 potassium in it. So a minimum number 1 makes a net minimum on this side 2, right? Because of the potassium here. Same here, if you have only 1, the minimum number possible, right? 1, but that makes 1 calcium, that's okay, but at least 2 nitrate on the left side. So, yeah, so this is also makes sense. So this is just 1 calcium and 1 carbonate that makes the 1 over here as well. So yeah, that's it. Okay. Makes sense, right? So we're done with the balancing. So we have 1 calcium, 1 carbonate, 2 nitrate, 2 potassium, 2 potassium, 2 nitrate, 1 calcium, 1 carbonate. So 1, 1, 1, 2. Okay. So if that is the case, only thing now you have to think about is the solubility on your product here. Oh, I mean, you can think about this one too. This is aqueous for sure, right? Because of the nitrate. Everything that pair with the nitrate is soluble, aqueous. Potassium, always group 1, always aqueous, always dissolving water. So these two are obviously well dissolving water, so it can be mixed well in the mixture. This one. So they have a potassium nitrate, which is water soluble or not? Soluble. Because of the potassium and nitrate, they're both really well water soluble ions. Okay, and then think about this one. Calcium is group 2. I hope you guys remember this. If you're in a group 2, which is the second column in the periodic table, it's not so much water soluble, like 50-50, maybe not even 50. So not so much. And the carbonate is also not really good one to be dissolving water either. So these two combination makes quite not so much water soluble in compound, so it also precipitate too. So calcium carbonate is also not so much soluble in water, so they come out from the homogeneous mixture and then makes some precipitate, which is our calcium carbonate. It's precipitation happening. So if I ask you to write the lead ion equations, what you really need to do is try to get 1 calcium goes on with the 1 carbonate anion, which are initially dissolving water in aqueous phase. Now they're paired up together, makes the 1 ionic compound, which is not so well water insoluble. They come in precipitate in solid phase. Okay, so this is your net ion equations. Okay, so as you can see, the potassium nitrate didn't do anything. They're just all both soluble in here and here. So the spectral ions in this here will be potassium and the nitrate ions. Okay. Kind of makes sense? Good. Okay. So, all right. So then, I promise you I'll do more of this one, obviously in the review sessions that we did for exam 1. So. I think we have exam 2 early April, so I think 7th and 9th of April. So we still have quite a time. And we also have spring break coming, right, next week. Oh, there's one more thing. I'll also try to do the extra credit on Monday as well, just for the next week. Maybe if you have if you want to watch the Friday lecture on YouTube, you can comment on Monday. Anyway, so I'll move on. So try to go into the next type of reactions you can see in the aqueous solution here. Before we get to that part, I want to point out something terms first, and then we can move on to the next type of the reaction you may see on the aqueous solution mixture. So this one is what we call acid and base definition. Okay. So in here, we're gonna use mainly three type of definition of how we define acid or base. Okay. So the first one we use Arrhenius definition for acid and base. So in Arrhenius acid and base, the acid means they are hydrogen cation donor. So in Arrhenius definition, any compounds that can donate the hydrogen cation, that is our Arrhenius acid. Okay. In Arrhenius definition, the base is the one that donate the OH minus. So if there is any compounds that donate the OH minus hydroxide anion in the solution, that is our Arrhenius base. Okay, over here. This is actually okay for most of the chemical reactions, but for there's certain type of exceptional case, we may sometimes have to use the other definition is what we call Bronsted-Lowry definition. Okay, it's almost same, but slightly different. So we can cover all the other exceptional case. We cannot use the Arrhenius definition anymore. And in here, the acid is the one that donates the proton. So proton donor is your Bronsted-Lowry acid. Okay, and in Bronsted-Lowry definition, the base is a proton acceptor. Or you can say they steal the protons from somebody. Okay, so well, we're gonna talk about this one, these two most of the time. There's another one. We call Lewis acid and base. This is even can cover any type of a chemical reaction, most of the chemical reaction as an acid and base reaction, by using electrons. In Lewis acid is the pair of electron acceptor. So what I mean by this one is if you accepting the electrons, which is negative, right? The electron is negative charge. That is the same as you giving something that is positive to the other. So something negative coming into you, that is the same action you do giving off something that is positive. Does it make sense? So Lewis acid is just a different way to look at it, but with an electron, pair of electrons. So and here, once you say the proton, which is what? Positive charge. Okay, positive charge. So in Bronsted-Lowry definition, it says acid behave like a proton donor, but it's a similar concept as they behave like an electron pair acceptor, because it's all the charge difference there. So in that way, the Lewis base will behave like what? Electron pair donor. Okay. This is really good sometimes because whenever you look at the all typical organic chemical reactions, you're going to see that all just movement of the pair of electrons or one, the radical reaction and so forth, they'll actually tell you some type of compound may behave like acid and base. Even we cannot do it with these two definitions. But the problem is this is too broad concept to apply which one is acid and base. So normally in chemistry, this is the most famous one, Bronsted-Lowry. So if that compounds accept or donate the proton, that's how we can say, oh, this compounds behave like acid or base based on here. Or you can also use this one, but there's some limitations. I'll tell you later, maybe this semester or Are you guys taking Gen Chem 2? Yeah. Then you'll get there to why it's so needed big time next semester. But anyway, so let's focus on these two. You don't have to worry about this one too much. Okay. So I'll give you some examples. In Arrhenius definition, instead of they say the proton, they said hydrogen cation, because a hydrogen cation is simply same as proton. If you think about the hydrogen, which is what? Atomic number 1, means there will be one proton in hydrogen. So when it's have a neutral hydrogen, that means you have a one proton. You should also have a one negatively charged electron. So they can pair up together to become neutral elements, which is hydrogen. Okay, but if that hydrogen loses the electron, only thing that left is just one proton. So hydrogen cation and the proton literally same thing. It can't, yeah, makes sense, right? So anyway, so let's try to do this one. Okay. So first of all, can you guys name this one? This is what we learned before. This is nitrate, but this is a polyatomic anion part, oxy acid type of thing. So it'll be nitric acid, right? You guys remember this? Nitric acid over here. And this is sodium, this is OH minus, so this is perfect, sodium hydroxide. So this is what happens. So this is the sodium hydroxide, perfect. Okay. So think about this one. I'll show you how it works and what might be the product over here, but just think about in water. This is obviously in aqueous phase because nitrate and hydrogen, which is a good combination to be dissolved in water well. Sodium hydroxide anion is actually not so water soluble, but because of the sodium is actually group 1, right? So there's no exception, always soluble in water. So even though you have a quite not water soluble anion, which is a hydroxide anion, still will be soluble in water. Okay, so it will be aqueous too. So if this is the case, what happens to this one here is in aqueous phase, they're actually in ion form. So whenever you break down to the ionic form, which is hydrogen cation and nitrate anion. So this is what actually looks like. I put it in here, an HNO3 in aqueous phase, but what it actually in the form of the mixture is H plus and NO3 minus. That's what they are really in the water. Okay. So this is what happened here. And this one is the same. One sodium cation and one hydrogen anion now just hanging in water because they're surrounded by water molecules. So if you guys remember what we discussed last time was the solute and solvent. Solvent is the one that is much high numbers of that in mixture. So they solvent molecule because it's a lot more than solute. They're just surrounding the solute. So if that happens, that means the solute will become dissolved in solvent molecule, which is what? Solvation. In this case, they're now in water, so we call this hydration. So anyway, so if that is the case, what happens to this one here? We're gonna also pair up this and this and this and this separately. And in case, if you look at this one here, this one now in water, H plus hydrogen cation and N minus. So this is your acid right here. You see it, right? Because it breaks down to the hydrogen cation and nitrogen anion that give us what? Lots of proton in water. Okay? So that makes this one acid. Like we talked just before. Okay? Makes sense, right? How about this one? So we have a sodium hydroxide here. Once again, when in the ionic form, there's a sodium cation, hydroxide anion. So in that case, this compound will give us lots of hydroxide anion, which is what? Base, perfect. So in this case, we're actually mixing not just the compound, but acid and base together. We call this neutralization. Okay, so you have something that is acidic, something that is basic. If you just come it together in the same container in the mixture, you're going to see some neutralization because it is to hydrogen cation, hydroxide anion will make water, which is neutral in pH level in mixture. So once it's acidic, once it's basic, but all together become neutral. if it's the same quantity on both sides. Okay, so that's why they'll in product side they become water. Okay, and then you're going to have what? Sodium nitrate, which will be also what? Soluble in water. Okay, so what it actually happened was this one. This is your net ion equation. So whenever you see this type of acid-base neutralization process, probably not necessarily you see any signs of the precipitations, nothing come up from the mixture, but you still need to think about this may happen, which is water formation, right? Neutralization, and then this is still your net ion equation. This is what actually happened in the mixture. It doesn't seem on the outside, nothing happens, right? But on the inside, you actually see the formation of the water, so you just don't see it in the naked eye. But this is what happens when you find out if it's acid and base coming together, making some neutralization process. You get a lot of water, which what actually happened in the mixture. Because the sodium and nitrate stay in the ionic form. Actually, they didn't do anything, but these two make the water. So H plus plus OH minus makes water. That is the net ion equation for any types of the acid and base neutralization reactions. So even though there's no precipitate, they're all soluble in water. If we use the acid and base, you still need to find the net ion equation, which is this one. Makes sense, right? Do you have any questions? Okay, so yeah, let's try another one. Okay, let's try. Okay, can you guys try this one maybe? Yeah, let's try to this one. Okay, and then I'll give you about 2 minutes and see what you can do. Okay. Okay, about 1 or 2 minutes. Yeah, it's pretty much the same here. We're just gonna do the double displacement, but see if it's acid or base, and if there's water. Let's take a look at it. Okay. All right. So if that is the case, once again, I'm gonna do this one and this one, and in ionic form, this will donate us a lot of hydrogen cation. This is the one donates OH minus. So I know these were to make what? Water. So there's water there. Okay. And then the potassium and sodium, the chlorine will can pair up. And also soluble in water here. So that's pretty much it. So your net ion equation is still the same that we just did. Okay. Yeah. Okay. Same net. So acid and base neutralization process always the same net ion equations. Hydrogen cation comes in with the sodium hydroxide and then makes hydroxide anion and makes water. Okay. So yeah. So in here, spectral ions are just potassium and chlorine, potassium cation and chlorine anion. Okay. Okay. Let's do one more. Okay. 1 or 2 minutes. Oh, yeah, this is plus 1, sorry, minus 1, minus 1, yeah, plus 1. I think you guys know by now, but. So if you look at the periodic table, you may see if it's a positive charge, negative charge, and what charge it may be there. Except the transition metal one. Transition metal one, you only know by looking at the numbers of an anion that are attached to that neutral compound. So, so same here, right? Pretty much. So it will be water here, okay? This is water, and then you just have calcium bromide, but it just didn't do anything much anyway. So most importantly, just water formation, which is the neutralization. Okay, makes sense, right? I think I can move on now. Okay. All right. So we have quite some idea what this acid and base are and how they do the neutralization together. It's simply double displacement we have been doing for the chemical reaction anyway. So we have something what we call acid and carbonate reactions. Okay. So that simply means that any compound that donate the hydrogen cation. So for example, you can try HCl, and it comes with the calcium carbonate over here, okay, so which is there. So if that is goes over there, okay, so what happened to this one is you're going to have a formation of water, okay. This is the calcium. The one thing that is kind of special about this one is you're gonna see some the gas formation, which is a carbon dioxide over here. Okay, so this is why this is kind of special. So if you have any compound that has the carbonate inside in the compounds, if they interact with something that we consider acid, like HCl, this is also good acid compounds, right? And then they can make the water and the carbon dioxide, but this carbon dioxide in gas phase. So they will make a lot of gas. So if you try to react any compound with carbonate with some acid like HCl, bromic acid, chloric acid, fluoric acid, any type of acid, will produce something type of the gas that is the carbon dioxide coming from the carbonate. Okay. So that's pretty much it. Do you know? I'll finish here, but just I don't know. Don't try this at home. Maybe if you want to do it, you can try it in a safe condition in the kitchen. If you go, do you guys like to cook? Someone? Okay. You have a vinegar in your kitchen? Vinegar? So vinegar is simply one type of a diluted acetic acid. So it's one type of a very slightly acidic solution. Not so strong, but it's a slightly acidic solution. I don't know if you have a baking soda in your house. So if you put a little bit of baking soda with the vinegar, they will make a lot of bubbles. That is carbon dioxide. You can easily find in the kitchen too. This is one type of the reaction we just talked to. It's very simple. Anything that with the baking soda is sodium bicarbonate. So that also baking soda is also the one that has a carbonate. This one, sodium bicarbonate. So if you deduct the acid from the acetic acid, okay, this comes to there, and water too. Well, we have to balance it, but that is why you see the carbon dioxide. That's also one of your acid carbonate reactions. So I'll talk more on the Monday, but I'll stop here today.